You're here today because I assume you're interested in machine learning, and in particular in applied machine learning. Now, we all know it's a good time to be in the field, but what I want to try to convince you of in this talk is that it's not just a good time to be in machine learning, it's actually a spectacular time, because we may be on the brink of what could reasonably be called a revolution, a new era in computation. Before I explain what I mean by that, let me first tell you what I'm not talking about, and I'm not talking about so-called artificial intelligence. There is a long-standing aspiration, going back certainly as far as Turing, more than 7 decades, to understand whether we can create machines that have all the rich cognitive capabilities of the human mind. It's a fine scientific aspiration. If we ever achieve it, it will have profound implications for humanity. No one knows when that day may come. It doesn't appear to be just around the corner, but who knows, there may be a breakthrough tomorrow. I'm going to talk about something quite different, but something which I also think is enormously profound. And I'm going to explain this by means of an analogy, and the analogy is with the development of computer hardware. So here's a very brief prodded history of computer hardware over the decades. So a very early example of computer hardware, of course, was Charles Babbage's differential engine and analytical engine, and the technology was based on brass gear wheels. So really, he was a visionary whose ideas were way beyond the technology of the day, and it wasn't really very practical. So it really wasn't until the development of the thermionic valve, or the vacuum tube, that large-scale computers of any seriousness really became practical. And compared to those brass gear wheels, of course, these valves were very much faster and very much cheaper to produce. And then there was another breakthrough, the development of the transistor. The components got a lot faster, they got a lot smaller, they consumed a lot less power, and very importantly, they became a lot more reliable. And then perhaps the next development was the integrated circuit, putting multiple transistors on the same piece of silicon. And over time, the number of transistors on that piece of silicon grew and grew until we could put an entire computer on one chip. And then we learned to put multiple chips, multiple cores on the same piece of silicon. And today, we've gone way beyond even that with data centers, huge buildings full of racks and racks and racks of computation. So it's clear that over the passage of time, computer hardware has got faster, it's got cheaper, it's got better. But the key thing is that that progression was not uniform. There was a singular moment. There was a very specific piece of technology which was developed, which changed everything. Up until that time, the development of computer hardware is what I will loosely refer to as linear, meaning it's sort of linear or polynomial growth. Each development builds on what's gone before and is faster, better, cheaper, but in a relatively steady sort of way. And then along came a piece of technology called photolithography. And photolithography changed everything. Because instead of making the components of the computer and then assembling them, instead, in photolithography, you print the whole computer in one go. Or maybe it's 30 passes or something like that, but it's a finite number. And in that finite number of steps, that small number of steps, you produce an entire wafer full of computers. And this morning, we just had a wonderful tour of the clean rooms and the fabrication facilities here at EPFL, very impressive, possibly even some of the best facilities of its kind in Europe, and it was wonderful to see that. That technology had a spectacular effect, because as you make the transistors smaller, they get cheaper. Think about printing a sheet of paper. When the font gets smaller, you get more letters for the same cost. Transistors are interesting, though, because when they get smaller, they switch on and off faster, and that means they're better. So we had a technology that, as you make it smaller, not only does it get cheaper, it gets better. And not many think about cars. Imagine if a better car was cheaper, what that would do to the car industry. Well, this ability to make things smaller and faster and cheaper, of course, is known as Moore's law, and it has a very particular characteristic. It's an exponential growth. The number of transistors on a piece of silicon doubles about every couple of years or so. And by the way, that's continuing today. Moore's law in its true sense has not slowed down. What we've hit, rather, is a power limitation. As you switch these transistors on and off fast, as they get packed more and more closely together, the heat density eventually becomes the limitation, not the number of transistors. But this was a singular moment in hardware, and it's why companies like Microsoft exist, it's why we have the internet, it's why you have a supercomputer in your pocket. It's all to do with Moore's law and the very, very special characteristic of exponential growth as distinct from just polynomial growth. So I believe something similar might be happening in the world of software. So this is the world's first software developer, Ada Lovelace, and she wrote software for Babbage's analytical engine. And she wrote what we might call very low-level software. She had to specify precisely where every gear wheel would be at every step. Since then, software development, the efficiency with which we can produce software, has improved year on year. This is an example of an integrated development environment. So today, a software developer will call a line of code, which will invoke thousands of lines of code written by other developers. There are technologies such as compilers and interpreters and debugging tools and all sorts of technologies which allow developers to build on the work of others and which increase their productivity enormously. But that growth has been essentially linear until today. So some new technology has come along, which is machine learning. And machine learning, I will argue, is radically different. It's radically different because instead of using human intellect to program the computer to solve the problem, we do something totally different. We write a very different kind of software. We write software that allows the machine to be adaptive, and then we train the machine using data. And that's profoundly different. It's so profoundly different, it's sometimes called software 2.0, meaning an entirely new concept in software and how we create software. This is an example from our lab. This is, it's not actually a neural network, it's a thing called a factor graph. This is a very elegant probabilistic model for making recommendations. Let's say you want to recommend movies to people. It combines techniques of collaborative filtering, comparing your likes and dislikes with the pattern of likes and dislikes across large numbers of other users, and inferring the probability that you will like some unseen movie, and then combining that in a very principled way with features of the user, perhaps their geographical location, their age, and so on, with features of the movie, the genre, the actors, and so on. And all that solved using a variational message passing technique. But the point is that we kind of use software 1.0, if you like, to code up the, in this case, the inference engine. But the actual solution to the problem, the way we get to recommend movies to people, is data-driven. Now, the interesting thing about data is there's sort of ever more data with the passage of each year, and I'll illustrate that by showing you a photograph of a data center. There's a Microsoft data center in North America, so I hope you can see the sort of car parks there and the scale of that building inside. Just imagine racks and racks and racks of thousands and thousands of computers. And if you look at the top of the picture, you'll see the data center is actually being expanded. There's some building work going on. And if we swing around and look at the other side, you'll see it's quite extensive building work. Microsoft, although Microsoft doesn't disclose the numbers, Microsoft is spending many, many billions of dollars every year building out new data centers. And they're called data centers, of course, because they store data and they compute with data. And the amount of data is certainly increasing. And there are quite a few studies that show the amount of data in the world is increasing exponentially. And interestingly, the doubling time seems to be about a couple of years. And there are lots of reasons for this, but you can get a sort of glimpse from this picture. We're instrumenting the world. Our cars have sensors, and those will be internet-enabled. We're instrumenting our factories, we're instrumenting our cities, we're instrumenting our bodies. The Internet of Things alone will account for tens of billions of devices that are internet-enabled. And that trend, that exponential growth in the amount of data in the world, looks set to continue for many years to come, in the same way the exponential growth of transistors held out for many decades. Now, why does that matter? It matters because in software 1.0, in traditional software, the rate-limiting step is generally the human intellect. It's the ability of the programmer to keep in their mind a complex algorithm. And one of the challenges of software engineering, of course, is to decompose things so that teams of people can work together collaboratively on tackling a big development project. But we all know that if 10 people can produce great software in a given period of time, you know that 1,000 people won't get there 100 times faster. In machine learning, the rate-limiting step is very often the data itself. And we know from the revolution in deep learning that in many cases it's the quantity of good data that's available that actually limits the performance of the system. So if you put those pieces together, we've seen that exponential growth of hardware led to the modern digital era. That was the digital revolution. Imagine what computers would be like if we only had linear growth. Something similar is happening in software 2.0, in machine learning. It's driven by data, it's limited by data, and the amount of data in the world is growing exponentially, and that exponential growth looks set to continue for many years to come. So given that, it's sort of hard to escape the conclusion that it's not just a good time to be in machine learning, that we may truly be at the dawn of a new era. I feel incredibly excited. I'd probably be even more excited if I was a graduate student at this point, but nevertheless, I'm glad still to be part of all of this. And we'll see which way it goes in the years ahead, but certainly this is a remarkable time to be in this field. Now, because we're talking about applied machine learning, I wanted to show you some examples of machine learning applications. And here I had the challenge of what to choose to show you. One way to think about this is to think about, obviously I'm going to show you examples from Microsoft, but you might ask yourself, well, what is Microsoft's mission? In fact, you might ask that of any big technology company. Fundamentally, what do they do? Well, Microsoft, as I'm sure you know, has undergone a major reboot, a refresh over the last few years. Our mission today is about empowerment. So Microsoft's business is to help others be successful and then share in that success. And the others there, according to the company's mission statement, is every organization and every person on the planet. So that means we have customers, we work in every domain, whether it's retail, whether it's aerospace, whether it's healthcare, whatever it might be. We engage with customers across all of those domains. And so we have applications of machine learning that really span pretty much the whole spectrum that you can think of. So rather than present an extremely long list that goes on for many days, I've chosen a particular domain, and I've chosen one that I'm personally very passionate about, which is healthcare. It's an area which many people believe is set to be revolutionized by data-driven technology. In many ways, we hope that it will be, because it urgently needs an overhaul. And it's an area that we have an increasing interest in Microsoft across all of our research labs, indeed across our product teams as well. But even that's quite a big domain, so I've picked just projects that we're working on in my lab in Cambridge in the UK, and even there I'm just going to show you a little sample. So here's one. This is a project called Inner Eye. This is something we've been working on for several years, so it's really at a very advanced state. And it's, as you can see, it's to do with medical imaging. It's tackling a very specific problem in medical imaging, which is the segmentation of tumors and the segmentation of vital organs. And we chose this specific application because it's a critical piece of workflow that's really very tedious and time-consuming, and where automation could really help the radiation oncologists do their job faster and better. And this arises because, sadly, about half the people in this room at some point in our lives will develop cancer, and of those, roughly half will have some form of radiation therapy. Now, when you get radiation therapy, the idea is to fire radiation at the tumor and kill the tumor and do the minimum damage to healthy tissue. So to do that, you need to know where the tumor is in 3 dimensions. You need to segment it. And so it's a very specific machine application, but one with, which is of tremendous potential benefit, because a radiation oncologist, this is Raj Jenner from the big research hospital in Cambridge, Adam Rooks Hospital, who's one of our collaborators. In his day job, he'll spend a lot of time, anywhere from 20 minutes up to several hours, going through a 3-dimensional MRI or CAT scan, layer by layer, and using a stylus segmenting out the tumor. It's very tedious, it's very boring, and it's not great use of his tremendous clinical skills. And so Inner Eye helps to automate that process of segmentation. So it uses machine learning techniques to segment, in this case, I think this is a glioblastoma in the brain, presents that to the radiation oncologist. That obviously just takes a second or two. And then the radiation oncologist then examines that, makes any small corrections they deem necessary, and then accepts that segmentation, and that goes on to radiation therapy planning. It can also be used for things like clinical trials, where you're monitoring the growth of a tumor, or hopefully the contraction of a tumor in response to treatment. Here's another project. This is one I'm very excited about. This is a collaboration with Microsoft Research in Redmond and an amazing company called Adaptive Biotechnologies, which is a Seattle-based company. They have some genetic sequencing technology that's very tuned to decoding the sequences responsible for so-called T-cell receptors. Now, your immune system itself is an amazing sort of learning machine. Your body synthesizes these white blood cells called T-cells, and these T-cells express on the surface little random protein sequences. And your body makes millions of these, and then it tests them to see if those protein sequences match your own body. And if there is a match, the cell is killed. So about half of all the white blood cells that are manufactured are then killed, and the rest are released into your bloodstream. And they patrol around your bloodstream waiting for a match. They might find a match when you have an infection. They might find a match when you have a cancer, and therefore you have unusual DNA circulating in your blood. And sometimes they'll find a match by mistake when you have an autoimmune disease. When a T cell finds a match, it does two things. It replicates, builds a big army, and it goes and attacks that invader. After the infection has gone away, some of those T cells continue to circulate, and that's where you get immunity from. It's your body's memory of the infections that it's had. Now imagine you're trying to detect an infection or, let's say, a cancer. One way you might hope to discover a cancer early on is taking a blood sample and looking for the DNA from the cancer. The challenge with that is it's like looking for a needle in a haystack. The signal is very, very small. It's very hard to detect. So what we're doing in this collaboration with Adaptive Biotech is to use that immune system, those T cells, as a kind of amplifier, to amplify by about a factor of 1,000,000 that signal of, let's say, early stage cancer. Now that's the great news. The T cells provide this huge amplification, and that's exciting because if you can detect cancers early, then the prospects for successful treatment are very much better. Likewise with infections. Imagine a blood sample. The dream one day is that you'll take a blood sample, you'll be able to sequence it using Adaptive Biotech's sequencing technology, sequence the T-cell receptor genes, and then in some way apply machine learning and print out the diseases. First of all, a list of all the diseases you've ever had since you were born, but also anything that you have at the moment, including perhaps early stage cancers. And so the dream here, the moonshot, is to produce a universal blood test. But why do we need machine learning? Well, we need machine learning because what the sequencers measure are these random little proteins on the surface of the T cells. And we don't in advance have any idea of how they correspond to disease. So the goal of this collaboration is to collect data on a huge scale and to use machine learning to try to understand how to reverse that process, how to go from the T cell receptors to antigens and to disease. And what's all this got to do with Microsoft? Why is Microsoft involved in this? Well, two reasons, but only two reasons. There are only two things that we bring. The first is our cloud-scale storage and compute, and the second is our expertise in machine learning. Everything else is done through collaboration. So this project is in its early stages. The machine learning problems here are very, very challenging. We really don't know whether this can be solved or not. We're going to start with a small number of diseases, the ones we think might be the easiest, and we'll take it from there. So it's a lovely example of a moonshot, but with some nice goals along the way. I'll just briefly mention one other example. This is one of our most ambitious projects. What you see here is a photograph taken in Microsoft's first ever life sciences wet lab. We opened that in our Cambridge building a couple of years ago. This is run by our biological computation group. And the goal here is to view the molecular processes that happen inside cells as computation, and then to use the tools and power of computer science, including machine learning, to think about how we can modify that computational process to achieve specific goals. It might be the eradication of diseases, it might be improving the yield or the drought resistance of crops, whatever it might be. Today, that's done in a process that's called so-called genetic engineering, which is actually far from being an engineering discipline. You take a gene from one organism and drop it into another, and it works. I mean, imagine taking a processor out of a Mac and putting it in a PC and shaking it around, and it sort of boots up. It's incredible that it works at all, but it's a very hit-and-miss affair. So the goal here is to bring engineering discipline to that process. One way to think about this as a moonshot is to imagine a compiler for biology, which you specify the phenotype and you run some amazing piece of computation, and it gives you the genotype, which is a program which, when executed in a cell, gives rise to that phenotype. So I'm going to finish with a few brief announcements. Textbooks were mentioned in the introduction. Some of you may be familiar with this. This is those of you who are familiar with this will know that it's hardback. It's 750 pages long in full color. I once said that at least per kilogram, this is the best value machine learning book on the market. But it is kind of big and heavy to lug around. So the publishers have kindly agreed that we can make the PDF available. So a few weeks ago, we released the PDF. So if you go to ako.ms/prml, you can download the PDF. So I'm very pleased about that. And you should still buy the book, of course, obviously. Another thing that we're announcing this week, in fact, I'm in Switzerland for the whole week, is our Swiss Joint Research Centre. So we've long had collaborations between Microsoft Research and institutes in Switzerland. We are renewing this and relaunching it this week, in fact, over the next couple of days. And this is a deep collaboration between Microsoft Research, EPFL, and ETH Zurich. And this is a 5-year collaboration. We've already identified the first round of projects, and we're very excited at where this will go. And then finally, I'm just going to show you a picture of our lovely building. This is in Cambridge. We're in Station Road, right at the heart of Cambridge, in the sort of the technology quarter. A very beautiful building. And for those of you who are looking for opportunities, I'll just let you know that we are hiring. We have a booth outside, and we're very keen to hire interns, postdocs, researchers, and engineers. And with that, thank you very much.
Thank you, Chris. So we have time for a couple of questions. We have running mics. Please point out if you're interested to pose a question. I'll start with the first, and namely one that I posed to our keynote speakers yesterday. So you will be probably surprised, but I asked if they could go back in time to the beginning of their machine learning career. What would they tell themselves?
Do a startup.
Okay. All right.
Actually, it's quite interesting. My background actually was in physics,
Yep.
Field theory. Then I worked on the fusion program, and I sort of hit it lucky because I read about backprop. I mean, that's what inspired me. Jeff Hinton's paper on backprop, and I didn't know much computing. I persuaded my boss to buy a workstation, got the C code out of those PDP books, taught myself C, started hacking, and then started applying these techniques in the fusion program. Now, the fusion program, in its day, it was sort of the big data. There was a huge tokamak experiment down in Oxford, where I worked. It was the world's biggest tokamak. Had these amazing highest spatial and temporal resolution diagnostics. So they were flooded with data, and all the standard data techniques were linear. And so I came along with this hammer, this non-linear data analysis tool, and sort of cleaned up all sorts of problems, actually culminating in real-time feedback control of the plasma. But then, by that point, I was sort of hooked and decided that I wanted to sort of go beyond fusion and made the switch 30 years ago into the field of neural networks because I thought it could be interesting, and it turned out it was, that was actually a pretty good move, I think.
That was a good move, indeed. Good. Where do we have the mic? Can I see a hand, whoever holds the mic or has a question? Don't be shy. We're on time. No questions. I know, we know he's exceptionally clear. You all read, they all read your book, Chris, I'm sorry.
Well, there's nothing
no,
to be
there's
said.
a question. There's a question. The icebreaker question. It's on.
Okay, sorry. So thank you for your talk first. I so as you mentioned, like you worked in physics, and you mentioned work on biology and let's say what you call hard sciences and stuff. There's more and more this approach of using data-driven approaches to science, using machine learning to do what we cannot yet do with differential equations and very analytical solutions. What do you think is the future of science in this new era? Are we moving more and more towards having less analytical modelers and more data science, data-driven solutions?
It's a great question. So I sometimes distinguish between technology and science. So the goal of technology is to produce something that works. The goal of science is simply to gain better understanding. Now, 99% of what we do in machine learning, all of us in machine learning, is about technology. We're trying to solve practical problems. But these techniques can be used for science, and that is, as you pointed out, that's where I began my career in machine learning. And the goals there are different. So you can think of this more as sort of rich statistical analysis techniques. A nice example would be a collaboration we had over a number of years with the University of Manchester, in which we're trying to understand the factors by which children develop allergies and asthma. And so we used actually a probabilistic graphical model, a kind of souped up Kalman filter, you can think of it that way. We're running probabilistic inference over this temporal model and discovered natural clusters of children. It turns out there are 4 of these clusters, and one of them in particular has the characteristic that they acquire multiple allergies, and they do so relatively early in life. And it's that group that is twice as likely to develop asthma as the standard so-called atopy, which is the standard measure of propensity to develop asthma. So that was a very exciting paper, and we were really delighted by that collaboration. But the goal is understanding. So there it's not enough just to get an incredibly small error on the holdout set. That doesn't mean anything. So in a way, you're using the same kinds of techniques. You're getting data. You're probably using the same software and so on. But the goals are very different. So the way you have to approach it is very different, and you have to think about it in an entirely different way. But it is very exciting. I think there's a lot of potential to use these much richer, much more nonlinear techniques in scientific domains. But by the same token, it comes back to the question of interpretability that's often discussed in machine learning contexts. And this is an example where we mean interpretability in the sense of the actual developer of the algorithm being able to understand what that algorithm is telling you, because the goal is knowledge, not just good performance. But I think there's a lot of potential there. Yeah.
Any other questions? This is why it's called running mic.
Hello. The question about the choice of the research field. So you switched from physics to machine learning, and was there any? Was it because machine learning was popular, or was there something inside of this field that captivated you, like research in the brain, or like some other motivation?
That's a great question. And the answer I'd love to give you is I had this brilliant 30-year foresight that this was going to be amazingly important. I wanted to get in there early. The truth is completely different. The truth has a lot more to do with the film 2001: A Space Odyssey and the HAL computer, and just the sheer fascination of a machine that could be intelligent, a machine that could learn. And to be honest, I didn't find computers all that exciting, because although they were sort of magical, they're also very dumb. I mean, a computer's a thing that stupidly follows instructions very, very fast. And if you have the right instructions and do it fast enough, sort of magic happens. But the thing that got me interested in computing was neural nets and machine learning. I was inspired by the idea that we were building something that was sort of brain-like or vaguely brain-inspired that could learn. So it was those things that still motivate many people today that got me excited about going into the field. It turned out that here we are 30 years later, and the idea of machines that have the capabilities of the brain still seem a long, long way off. However, this is an incredible technology today that can be used for so many wonderful applications. So it was a good choice, probably for the wrong reasons. Yeah.
All right, do we take one more question right behind?
I think it's very interesting, your idea about using data, the volume of data as that we're under a new Moore's law. So are you thinking in more detail about trying to codify this a bit better into a Bishop's law?
Yeah, well, feel free to name it. I can't, but anybody else could. That's a sort of 50,000-foot view. I mean, it's not just quantity of data, it's really value of information that's in the data. And actually, one of the research projects that we have right now is thinking about that in, let's say, a scenario in which different entities, they might be individuals in a health setting or corporations or banks or something, are getting together and pooling their data, because we know that when you bring data together, you can do more than each data set alone. You now have to understand how much value did each party bring to the model or whatever prediction, whatever value you create out of that data. And that's not just how many points you have in the data, you know, how big is the data center in megabytes. I think actually one of the things I talked about last year at AMLD was the difference between there are two measures of the size of a data set, and they're often confused, but they're totally different. One is the computational size, which is how many bits does it take on disk, and the other is the statistical size, which is how much information does it convey to the specific question you're asking. And you can think of data sets, imagine Ohm's law. So you're measuring the resistance of a piece of metal. So you apply different voltages and you measure different currents, and you plot them on a graph. It's just one parameter. So it's a straight line through the origin, and you're just trying to find the slope. And so given a few measurements without much, with relatively low noise, you can get a very good measure of that resistance. You can predict the current for some new voltage very accurately with, say, a dozen data points. If I give you another 1,000,000 data points, your uncertainty goes down a bit, but it's already pretty small. It doesn't make a lot of difference getting the extra 1,000,000 points, because the first dozen were pretty good. So that's an example of a data set which is computationally tiny, a dozen pairs of floating point numbers, but statistically it's huge, because it's already taking you into this asymptotic region of value of information. And you can find other examples of data sets which are computationally huge but statistically very small. And I suspect that many of the data sets that we'll be dealing with are of that kind. You may have internet scale data, so computationally it's a vast data set, but because you're looking at such an enormous space and you're asking perhaps questions about individual people, for example, in a healthcare setting, it may be a statistically small data set. So, and in those cases, more data is always better. So even though you have huge amounts of data, computationally large data sets, you're still in this in a statistically small data regime, and therefore more data is always better. And therefore, if data really is growing exponentially and continues to do so, it should generate exponentially more value. That's the hypothesis, at least.
All right. Well, in the interest of time, we have to close here. But Chris, it's been a real pleasure. Thanks very much again.